Hi there, welcome to this Alchemist Chemistry video looking at the evolution of the Earth's atmosphere. So if you look at the table, you can see the composition of Earth's early atmosphere between 4.5 and 3.5 billion years ago. Lots of carbon dioxide, water vapor, and nitrogen gas present, with smaller amounts of ammonia and methane gas. This atmospheric composition is very different to that we find on modern Earth, and is more akin to other planets in our solar system, like Mars and Venus, for example. These places are inhospitable to life as it now is on Earth. Now, the evidence we have for the theories of the evolution of the atmosphere are reasonably limited, mainly coming from bubbles of gas trapped in ancient rock structures. But let's now outline that theory and development of the early atmosphere, where it came from and how it changed. So between 4.5 and 3.5 billion years ago, the Earth is incredibly volcanically active. There are volcanoes all over the surface of the planet. And not only are they spewing out hot rock and molten lava, but also gases. In the majority, this would be carbon dioxide, water vapor, and nitrogen. In the minority, this would be ammonia and methane. So clearly, these gases are forming that early atmosphere. So initially, temperatures on the planet are far too high for liquid water to ever exist. But over time, the temperatures begin to fall, and this allows gaseous water to condense into liquid water, and the first ever clouds are able to form. And of course, rain will fall from those clouds, but not like a sudden downpour like in the modern world, but it rains continuously for millions of years. And that rainwater falls into the cracks and crevices in the surface of the Earth and forms the early oceans. Now, finally, we can start to explain how the carbon dioxide levels on the Earth began to fall. Now there's lots of water everywhere, the carbon dioxide in the atmosphere can begin to dissolve into the liquid water in our oceans. And now that carbon dioxide reacts directly with water to form carbonic acid, slightly acidifying those oceans, but also trapping carbon dioxide in the water. And as temperatures drop and drop, more and more carbon dioxide can dissolve into the oceans. Strange idea, but liquids dissolve greater amounts of gases at lower temperatures. It's actually the reason you put your carbonated drinks in the fridge to keep them cold. Not because cold drinks taste great, but also it's helping to keep the carbon dioxide dissolved in the drink so it stays fizzy. Additionally, carbonic acid dissociates into hydrogen ions and carbonate ions. Now, those carbonate ions can react with metal ions in the water, like calcium ions, for example, to form precipitates, insoluble solids that can aggregate together into sediment, which will fall to the bottom of the oceans, onto the ocean bed, and build up layer upon layer, and eventually metamorphose into sedimentary rock, trapping the carbon, and therefore, again, we're decreasing the amount of carbon dioxide in the atmosphere and trapping it in different forms, like in those sediments, and therefore in that sedimentary rock that forms over millions of years of time. Fast forward to 2.7 billion years ago, and an important event occurs: the proliferation of algae and green plants. Now, both these organisms are photosynthesizers. They can use the light energy from the sun to convert carbon dioxide and water into glucose and oxygen. They're autotrophs, they generate their own food. But again, it's going to have important impacts on our atmosphere. It's going to simultaneously decrease the amount of carbon dioxide present whilst increasing the amount of oxygen present, drastically and radically altering the planet's atmosphere. Moving forward in geological time, we come to the idea that these plants and these organisms are living around, start to die out, get covered in sediment. Over millions of years, under extreme pressure and heat, as layers of sediment build up in anaerobic conditions, these dead organisms will convert into new materials. For example, dead compacted plant matter will, under extreme heat, extreme pressure, and in anaerobic conditions, convert into the fossil fuel known as coal. Or aquatic life forms will die and their calcium carbonate shells will be compressed under layers of sediment and will be converted into limestone. And also, microorganisms in the oceans can die, fall to the bottom of the oceans, be covered in layers of sediment, and over millions of years under extreme heat, extreme pressure, will convert into crude oil and natural gas. All of these compounds contain carbon, which is now trapped deep underground. So again, we are helping to decrease the amount of carbon dioxide in the atmosphere, trapping it and sequestering it in these new materials, in this coal, natural gas, crude oil, and even limestone deposits. Coming back to the importance of plants and algae, they have further helped to terraform and alter our atmosphere through creating so much oxygen. That oxygen can react with methane and ammonia in the atmosphere and undertaking oxidation reactions and converting the methane, for example, into carbon dioxide and water, and the ammonia into nitrogen and water, increasing the amount of nitrogen in the atmosphere, slightly increasing the amount of carbon dioxide, but also, importantly, decreasing the amount of methane and ammonia. And slowly but surely, the atmosphere creeps closer and closer to the modern composition that we are all much more familiar with and live in. And so finally, after 4.5 billion years of time passing, we come to the composition of the modern atmosphere. 78% of our atmosphere is nitrogen gas, an inert, unreactive gas that has built up slowly over time. 21% of our atmosphere is oxygen, coming from photosynthetic organisms like plants and algae. And in fact, if you go back to previous periods of history, like the Carboniferous period, the O2 levels were even higher due to the greater prevalence of trees on the planet. About 0.9% of our atmosphere is argon, an inert, unreactive noble gas, and only 0.04% of the atmosphere is carbon dioxide, and yet that is the root cause of many of our global warming woes. The other gases are known as trace gases, which are in minute amount. Thanks for listening, guys. I hope this video was useful to you. Take care. Bye for now.